In 2018, the European Space Agency released the final data from the most expensive thermometer ever built. The Planck satellite had spent 4 years in orbit around the second Lagrange point, 1 million miles from Earth, measuring the temperature of the oldest light in the universe to a precision of 1 part in 10 million. It mapped the cosmic microwave background, the radiation left over from the moment 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to fly free. The result was the most detailed portrait of the infant universe humanity has ever produced. Over 1 billion pixels, 6 cosmological parameters measured to better than 1%. The age of the universe pinned down to 13.797 billion years, plus or minus 23 million. The composition confirmed at 4.9% ordinary matter, 26.8% dark matter, 68.3% dark energy. It was the most spectacular confirmation of the standard model of cosmology ever achieved. And buried inside that confirmation was something that should not have been there. The Planck team found anomalies, not small ones, not ambiguous ones, features in the cosmic microwave background that the standard model, the same model Planck had just confirmed to extraordinary precision, predicts should not exist. A region in the constellation Eridanus, 5 degrees across, 70 microkelvin colder than it should be, 1 billion light-years wide at the distance of the last scattering surface, with no known structure large enough to explain it. A hemispherical power asymmetry, 1/2 of the sky carrying systematically more fluctuation power than the other, at 3 to 3.5 sigma significance. An alignment of the CMB's largest scale structures with the plane of our own solar system, so improbable that the physicists who discovered it called it the axis of evil. A near total absence of correlations at the largest angular scales, anomalous at 99.97%. Every one of these anomalies had been seen before in the earlier WMAP satellite data. The Planck team confirmed them. Different instrument, different orbit, different analysis pipeline, different team, same anomalies, and then in the way that institutions handle things they cannot explain, the anomalies were published in the appendices, noted as tensions, and the field moved on. You were never told about this. Not really. You were told the Planck satellite confirmed the Big Bang. You were told we know the age and composition of the universe with extraordinary precision. Both of those things are true. But here is what was not in the press release. Here is what did not make the summary paragraph that every news outlet copied from the ESA press kit. The cosmic microwave background, the single most important piece of evidence for the Big Bang, contains features that the Big Bang model cannot produce. And those features are not random. They cluster at the largest angular scales, exactly the scales where physics from before the Big Bang, if such a thing exists, would leave its strongest imprint. Jan Tauber, the ESA project scientist for Planck, said something when the data was released that has not received the attention it deserves. He said that Planck is painting a new picture of the universe that is pushing us to the limits of understanding current cosmological theories. That is a carefully worded sentence from a carefully positioned scientist, and what it carefully does not say is more important than what it says. It does not say the theories have failed. It does not say the anomalies are fatal. It says we are at the limits. And it says this about the most precise cosmological data ever collected. from the most expensive and sensitive instrument ever pointed at the sky, confirming a model that works flawlessly at small scales while simultaneously breaking down at the largest ones. If those patterns are noise, statistical flukes scattered across an otherwise perfect map, then we are remarkably unlucky. Multiple independent anomalies, each at 2 to 3 sigma or higher, all concentrated at the same angular scales, all confirmed by independent instruments, all uncorrelated with each other. The odds of that being coincidence are not impossible, but they are the kind of not impossible that keeps a particular kind of physicist up at night. And if they are not noise, if they are what a small but growing number of physicists believe they are, then what survived the death of an entire universe to reach our instruments is barely a whisper, a faint thermal signature in the oldest light we can see. Think about what that means for what will survive of us. This is the story of what the cosmic microwave background is actually showing us, and why physics has spent 2 decades refusing to answer the question. It starts with a hole in the sky that should not exist. In 2004, a team led by Patricio Villalba at the University of Cantabria in Spain was running a wavelet analysis on the first-year data from the Wilkinson Microwave Anisotropy Probe. WMAP had been operating at the second Lagrange point since 2001, and its all-sky temperature maps were the best the world had ever seen. Villalba's team was using a technique called the spherical Mexican hat wavelet, which is exactly what it sounds like, a mathematical filter shaped like a sombrero that you slide across the surface of a sphere to pick up features at a specific angular scale. When they applied it to the WMAP data, looking for cold spots, one feature screamed. It was centered at galactic coordinates 207.8 degrees longitude, negative 56.3 degrees latitude, deep in the constellation Eridanus. A follow-up paper by Cruz, Martinez-Gonzalez, Villalba, and Caon in 2005 nailed down the details. The spot's core spans roughly 5 degrees of sky, with a broader halo extending to around 20 degrees. At the distance of the CMB's last scattering surface, that corresponds to a physical size exceeding 1 billion light-years. The temperature deviation in the core averages about negative 70 microkelvin below the mean CMB temperature of 2.725 Kelvin. The deepest depressions reach negative 140 to 150 microkelvin. For context, typical CMB fluctuations have a root mean square amplitude of about 18 microkelvin. This spot is nearly 8 times deeper than the average variation in the entire sky. Only about 0.2% of standard Gaussian simulations produce a cold spot matching its morphology. That is a number that means something. Not quite at the level where you publish a discovery paper, but well past the level where you stop dismissing it as bad luck. The obvious explanation would be a void. Space is not uniformly filled with matter. There are enormous regions where galaxies are sparse, and a sufficiently large void between us and the last scattering surface would cool the CMB photons passing through it via the integrated Sachs-Wolf effect. Photons climbing out of a gravitational well in an accelerating universe lose more energy than they gained falling in. A big enough void would leave a cold imprint. In 2015, Istvan Sapudi and colleagues at the University of Hawaii found one. Using data from the Pan-STARRS telescope and the WISE satellite, they identified a supervoid aligned with the cold spot, approximately 1.8 billion light-years across, centered at a redshift of about 0.22. It was one of the largest structures ever found in the universe. But here is the problem. When you run the numbers on how much cooling the integrated Sachs-Wolf effect from that void can produce, you get about 10 to 20% of the observed temperature depression. The supervoid explains a fraction of the cold spot. It does not explain the cold spot. Something else is responsible for the remaining 80 to 90%, and nobody knows what it is. Ruari Mackenzie and Tom Shanks at Durham University pushed this further in 2017. Using data from the Dark Energy Survey, they confirmed that a supervoid exists in the direction of the cold spot, but showed that the void itself is not particularly unusual compared to voids predicted by lambda CDM. More importantly, they found that when they compared the galaxy density around the cold spot to random lines of sight through the survey, the cold spot region was not statistically exceptional. The supervoid is real, but it is not special enough to explain the temperature deficit. Something else has to be responsible. And this is where the explanations start getting uncomfortable. In 2007, Neil Turok and collaborators published a paper in Science proposing that the cold spot could be the imprint of a cosmic texture, a topological defect left over from a symmetry-breaking phase transition in the early universe. Textures are predicted by certain grand unified theories when a symmetry group is spontaneously broken in a way that allows for topologically non-trivial field configurations. When a texture collapses, it produces a characteristic hot ring surrounding a cold center, and the angular profile Turok's team calculated was a good match to the observed cold spot morphology. The profile matched, but textures are speculative, predicted by some grand unified theories, but never observed. And the symmetry breaking scale required to produce a cold spot of this magnitude pushes against limits set by other CMB observations. Cruz, Turok, and colleagues followed up in 2008 with a Bayesian analysis comparing the texture hypothesis to the Gaussian random field hypothesis. They found a Bayesian evidence ratio favoring the texture origin by a factor of about 2. Modest, not compelling. Enough to keep the idea alive, not enough to settle the question. And then there was the explanation that nobody in mainstream cosmology wanted to talk about. Laura Mersini-Houghton at the University of North Carolina proposed that the cold spot is a bruise, a scar left by a collision between our universe and another one. In the eternal inflation framework, our observable universe is one bubble nucleated within a larger inflating space, and other bubbles, other universes, can collide with ours. Mersini-Houghton argued a cold spot's profile is consistent with exactly this kind of collision, the imprint of something that existed beyond the boundary of our universe, pressing in. No consensus explanation exists. The supervoid is insufficient. Textures are unconfirmed. Bubble collisions are untestable with current technology. And the cold spot is still there, confirmed by Planck with even higher precision, sitting in the southern sky like a question nobody wants to answer. But the cold spot is not alone, and what surrounds it is worse. The cosmic microwave background is supposed to be statistically isotropic. That is the technical way of saying it should look the same in every direction. On average. This is not a minor assumption. It is the cosmological principle, the foundational axiom upon which the entire standard model of cosmology is built. The universe is homogeneous and isotropic on large scales. Every calculation, every parameter estimate, every prediction of the lambda CDM model depends on this being true. In 2004, Hans Christian Eriksen and colleagues analyzed the WMAP data and found that it is not true. One hemisphere of the CMB sky has systematically greater fluctuation power than the other. When Planck measured it with far smaller errors, the result held. The dipole modulation amplitude is A equals 0.073 plus or minus 0.010. The preferred direction points to galactic coordinates 217.5 degrees longitude, negative 20.2 degrees latitude. The effect is strongest at the largest angular scales, and its significance reaches 3 to 3.5 sigma, depending on the estimator you use. 3 sigma does not sound dramatic until you understand what it means in this context. This is not a noisy measurement of a distant galaxy. This is the most precisely measured radiation field in the history of science, observed by 2 independent satellites with completely different instruments, systematics, and analysis teams, and both of them see the same asymmetry, pointing in the same direction. The probability that this is a systematic error, a glitch in the instrument or the analysis, is effectively zero. It was the first thing the Planck team checked. They checked their beam asymmetries, their noise properties, their foreground subtraction, their map-making algorithms. The anomaly survived every systematic test they could devise. The probability that it is a statistical fluke in an otherwise isotropic universe is about 1 in a few hundred to 1 in a few thousand, depending on how you count. Not impossible, but uncomfortable, especially when you realize what this asymmetry means physically. 1/2 of the observable universe has measurably more structure, more variation, more unevenness in the primordial plasma than the other half. In a universe that is supposed to look the same in all directions at the largest scales, there is a preferred direction, a cosmic north and south. The universe is lopsided, and nobody can explain why, especially when you notice that the cold spot sits in the anomalous hemisphere, and especially when you notice what else is going on at the largest scales. In 2005, Kate Land and João Magalhães at Imperial College London published a paper in Physical Review Letters with a title that was deliberately designed to provoke. They called it The Axis of Evil. What they found was this: the CMB's temperature fluctuations can be decomposed into spherical harmonics, like notes in a chord. The lowest harmonics, the ones corresponding to the largest angular scales, define preferred planes and directions on the sky. In a statistically isotropic universe, these directions should be random, pointing every which way, uncorrelated with anything. Instead, Land and Magalhães found that the quadrupole and octupole, the 2 lowest non-trivial harmonics, define preferred planes that are nearly coincident with each other, aligned with the ecliptic plane of the solar system, and aligned with the direction of the CMB dipole. Schwartz and colleagues had already found the octupole planes orthogonal to the ecliptic at 99.1% confidence, and their normals aligned at 99.6% confidence. Land and Magalhães pushed the analysis further and found the alignment extended all the way to the 5th multipole, rejecting statistical isotropy with a probability in excess of 99.9%. Lawrence Krauss, the theoretical physicist and public science communicator, said something about this that is worth sitting with. He said there is no way there should be a correlation of structure with our motion of the Earth around the Sun. That would say we are truly the center of the universe. That is not a fringe interpretation. That is a straightforward reading of what the data shows. Either the largest scale structure of the cosmic microwave background is aligned with the plane of our solar system, which would violate the Copernican principle and everything we believe about our place in the cosmos, or something about the way we measure and analyze the CMB at the largest scales is fundamentally wrong, or there is physics operating at those scales that we do not understand. Planck reduced the significance somewhat to roughly 2 to 3 sigma, but the alignment persists. It was not caused by foreground contamination. It was not caused by the instruments. It is in the data. The fourth anomaly receives less public attention than the others, but may be the most statistically significant of all. The 2-point angular correlation function of the CMB, which measures how much the temperature at one point on the sky is correlated with the temperature at another point separated by a given angle, should follow a specific curve predicted by lambda CDM. At small angular separations, it does beautifully. But at separations larger than about 60 degrees, the correlations nearly vanish. They are essentially zero. The probability of this happening in a lambda CDM universe is 0.03%. That is the 99.97% figure. Kopy, Hutterer, Schwartz, and Starkman have made this point repeatedly, most notably in a 2009 paper in Monthly Notices and their 2016 review. They describe it as the most significant anomaly at the largest scales. What this means physically is that the two halves of the sky, the parts separated by more than 60 degrees, show almost no memory of each other. In the standard model, correlations at all angular scales are established during inflation, when the observable universe was small enough for every part of it to be in causal contact. The fact that the larger scale correlations are missing suggests that something is wrong with how inflation established those correlations, or that the universe is finite and smaller than the distance to the last scattering surface, which would cut off the largest modes, or that there is pre-inflationary physics imprinted at those scales. Every one of those explanations is deeply uncomfortable for the standard model. And here is the part that should disturb you. These anomalies, the cold spot, the hemispherical asymmetry, the axis of evil, the missing large angle correlations, are not different expressions of the same underlying problem. They have been tested for correlations with each other. They are largely independent, different anomalies pointing to different problems, all at the largest angular scales. The group that has done the most to establish this, Schwartz, Kopy, Hutterer, and Starkman, sometimes referred to informally as the SKS group, published a definitive review in 2016 in Classical and Quantum Gravity, making exactly this point. Dominic Schwartz is at Bielefeld, Craig Kopy at Case Western Reserve, Dragan Hutterer at Michigan, and Glenn Starkman at Case Western Reserve. They have been studying the large angle CMB anomalies for over 15 years, accumulating what amounts to the most comprehensive case that something is genuinely wrong at the largest scales. Because the anomalies are uncorrelated, their combined statistical significance exceeds that of any individual anomaly. You cannot dismiss them as one unlucky draw from the cosmic lottery. They are multiple unlucky draws, each independent, each confirmed by independent instruments, each concentrated at the angular scales where the standard model's predictions are supposed to be the most robust. Starkman has been particularly blunt about the significance of this. He has argued that if you take the anomalies seriously, the evidence against statistical isotropy at the largest scales is at the level of 3 to 4 sigma, depending on how you combine the individual measurements. That is not discovery-level significance, but it is the level at which, in any other area of physics, you would be building dedicated experiments to investigate further. In particle physics, a 3 sigma result triggers follow-up searches. In astrophysics, a 3 sigma signal from a new type of source triggers telescope time applications. In cosmology, at the largest angular scales of the CMB, 3 to 4 sigma triggers a shrug and a footnote. The double standard is remarkable, and it is not accidental. These anomalies, if taken at face value, challenge the cosmological principle. And the cosmological principle is not just another assumption, it is the assumption. Everything else rests on it. And those angular scales, the very largest ones, are precisely where physics from before the Big Bang, from before inflation, from before whatever happened at the moment this universe began, would leave its fingerprint. The CMB is not a baby picture. It might be a crime scene photograph. And the investigation has barely begun because the people in charge of it cannot agree on whether the crime actually happened. But there is someone who claims he found the murder weapon, and the story of how he found it, why the establishment rejected it, and what it implies about the fate of everything you have ever known is where this gets worse. Roger Penrose was 87 years old when he published the paper that he believed would change the way humanity understands the beginning of the universe. It did not, or rather, it has not yet. Whether it eventually will depends on questions that the next generation of experiments may answer within the decade, and on questions about the nature of evidence itself that physics has been arguing about since the Bohr-Einstein debates. To understand what Penrose found, you need to understand what Penrose is and what he is not, and the unusual space he has occupied in physics for 70 years. He was born on August 8, 1931, in Colchester, England, into a family so intellectually accomplished, it borders on absurd. His father, Lionel Penrose, was one of Britain's leading geneticists. His mother, Margaret Leeds, was a physician. His brother Oliver became a theoretical physicist. His brother Jonathan became a chess grandmaster, winning the British Championship 10 times. Roger himself is not a cosmologist. He is not an astrophysicist. He is a mathematician who wandered into physics in the 1960s and never entirely left. Though physics has never been entirely sure what to do with him. He describes himself as occupying an uncomfortable middle ground. To physicists, he is a mathematician. To mathematicians, he is a physicist. He thinks in pictures. He draws diagrams. He has said, at a science museum lecture in London, simply, I like to draw pictures of things. When he was a child, he was moved down a class because he worked too slowly. The school interpreted this as inability. It was, in fact, the opposite. He was seeing things the other students were not, and it took him longer because what he was seeing was more complex. This matters for the story because CCC is, at its heart, a visual insight. It is the kind of idea that comes from someone who sees geometry before they see equations, who thinks about the shape of space-time before they think about the numbers that describe it. No one trained as a standard cosmologist would have proposed it. It required someone who spent decades thinking about conformal boundaries, about the causal structure of space-time, about the way light cones behave near singularities and at infinity. It required, specifically, Roger Penrose. In 1965, Penrose published a paper in Physical Review Letters that would eventually win him half of the 2020 Nobel Prize in Physics. The paper was titled Gravitational Collapse and Space-Time Singularities, and it was only 3 pages long. In those 3 pages, Penrose introduced a concept called a trapped surface, a closed, 2-dimensional surface from which light cannot escape in any direction, and proved that if a trapped surface forms, then general relativity guarantees the formation of a singularity, a point of infinite density and curvature, regardless of the symmetry of the collapsing matter. Before Penrose, physicists could argue that black hole singularities were artifacts of the simplifying assumption of perfect spherical symmetry. Carl Schwarzschild's 1916 solution, which first described the black hole, assumed a perfectly spherical, non-rotating collapse, and it was plausible that real collapses, which are messy and asymmetric, might avoid the singularity. After Penrose, they could not. The singularity was real. It was a theorem. It followed from the geometry of space-time itself, not from any special symmetry. Stephen Hawking, then a doctoral student at Cambridge, recognized immediately what Penrose's techniques could do if you reverse the direction. If a collapsing star inevitably produces a singularity in its future, then an expanding universe run backward in time inevitably had a singularity in its past. Hawking and Penrose developed the singularity theorems of the late 1960s and early 70s together, proving under very general conditions that the Big Bang was indeed a genuine singularity, not an artifact of symmetry assumptions. Together, their work became one of the foundational results of modern physics. They shared the 1988 Wolf Prize. In 1994, they staged a famous series of debates at Cambridge's Isaac Newton Institute, modeled on the Einstein-Bohr debates, published as The Nature of Space and Time. A reviewer described it as the title bout of the World Professional Heavyweight Theory Debating Society. They disagreed on almost everything philosophical. Hawking was a positivist who believed physics should deal only in observables and probabilities. Penrose was a realist who believed in an objective physical reality independent of observation. But on one point they agreed, and it was a point that would become crucial to everything that followed. They both believed that black holes destroy information. This matters because of what Penrose did next. In 2005, he proposed a framework called Conformal Cyclic Cosmology, published formally in the proceedings of a 2006 physics conference, and later in his 2010 book, Cycles of Time. He called it an outrageous scheme, a crazy scheme. He was not being modest. He was being accurate. Here is what CCC proposes. The universe does not happen once. It happens over and over in an infinite sequence of cycles that Penrose calls aeons. Each aeon begins with a Big Bang and ends not with a collapse, not with a big crunch, but with an exponentially expanding, increasingly cold, increasingly empty future driven by the cosmological constant, what we call dark energy. After perhaps 10 to the 100th power years, every black hole has evaporated through Hawking radiation. Every massive particle has either decayed or lost its mass. All that remains are photons and gravitons, massless particles traveling at the speed of light. And here is the key insight, the one that only a mathematician who thinks in pictures would have seen. Massless particles do not experience time. They do not experience distance. For a photon, the entire history of the universe, from emission to absorption, happens in a single instant. A universe populated entirely by massless particles has, in a precise mathematical sense, lost track of scale. There is no clock, there is no ruler. The difference between infinitely large and infinitely small becomes meaningless. Penrose realized that this state, the infinite future of a dead universe, is mathematically identical to the conditions at a Big Bang. Both are dominated by radiation. Both are conformally flat, meaning they preserve angles and light cone structure even though they disagree wildly about distances and times. Using a branch of mathematics called conformal geometry, which studies the properties of shapes that are preserved under angle-preserving transformations, Penrose showed that you can smoothly attach the infinite future of one eon to the Big Bang of the next. The boundary between them, which he calls the crossover surface, is seamless. Massless particles pass through it without noticing. The mathematical operation is called a conformal rescaling. You take the metric of space-time, the mathematical object that tells you the distance between any 2 points, and multiply it by a smoothly varying function. Distances change, times change, sizes change, but angles are preserved. Light cones are preserved. The causal structure of the universe, the web of which events can influence which other events, is identical on both sides of the crossover. For massless particles, which travel along light cones, the rescaling is invisible. They do not experience it. They cannot detect it. For them, there is no boundary. This is a genuinely radical idea, and it is important to understand just how radical it is. Penrose is not saying the Big Bang might not be the beginning in some vague philosophical sense. He is saying there is a precise mathematical transformation that maps the infinite future of one universe onto the initial singularity of the next, that this transformation preserves all the physical content that massless particles carry, and that the resulting cosmological model makes testable predictions. The math is published. It has been checked. The predictions may or may not be confirmed by data, but the framework itself is not speculation. It is geometry. What we call the Big Bang is not a beginning. It is a transition. The birth cry of one universe is the death rattle of the one before it. The theory was motivated by what Penrose considers the deepest unsolved problem in all of cosmology, and it is a problem that most physicists are content to ignore. The Big Bang had extraordinarily low entropy. Entropy, loosely speaking, measures the disorder of a system, the number of microscopic arrangements that correspond to the same macroscopic state. The second law of thermodynamics says entropy always increases. The universe today has far more entropy than the early universe, which is why time flows in one direction, why you remember yesterday and not tomorrow, why eggs break but do not unbreak. But if entropy always increases, then the Big Bang must have had fantastically low entropy. And Penrose calculated just how low. The probability of the universe's initial state occurring by chance is approximately 1 in 10 to the power of 10 to the power of 123. That is not a large number. That is a number so large that the entire observable universe does not contain enough particles to write it out in full. It is, in Penrose's view, the single most improbable fact about the universe, and almost nobody talks about it. Inflation does not solve this problem. Inflation requires its own special initial conditions, a sufficiently smooth patch of space with the inflaton field at the right value. And Steinhardt and Ijaz have shown that those initial conditions are themselves finely tuned. CCC offers a different answer. The entropy at the Big Bang is low because the previous aeon's black holes systematically destroyed gravitational degrees of freedom as they evaporated. Gravitational entropy, the entropy associated with the clumping of matter under gravity, dominates the universe's entropy budget. Black holes are the maximum entropy states of gravitational systems. When they evaporate through Hawking radiation, those gravitational degrees of freedom are eliminated. The entropy is not reset to zero, but the gravitational component, the overwhelmingly dominant component, is removed. The result is a crossover surface with low enough entropy to produce the conditions for a new Big Bang. This requires that information is genuinely lost in black holes, not scrambled, not encoded in subtle correlations in the Hawking radiation, but destroyed. This puts Penrose in direct opposition to the mainstream of quantum information theory, which insists on unitarity, the principle that quantum evolution is reversible and information is always preserved. When Penrose says black holes destroy information, he is not making a minor technical claim. He is rejecting one of the foundational principles of quantum mechanics, and he knows it. He and Hawking both defended this position for decades against the majority of the field, and CCC makes a specific, testable prediction about what should survive the transition between eons. In the previous aeon, over timescales almost too long to comprehend, supermassive black holes swallow their surrounding galactic clusters and then slowly evaporate through Hawking radiation. Each evaporating black hole radiates energy over perhaps 10 to the 106th power years. Through the conformal squashing of the crossover, all of that radiated energy, the entire output of a black hole that once consumed a galaxy, concentrates at a single point on the boundary surface. Penrose named these points Hawking points, after the man whose 1974 prediction of black hole radiation made the entire mechanism possible. The photons from a Hawking point do not become free-streaming until recombination, 380,000 years into the new aeon. By then, they have scattered and spread into a disk roughly 4 degrees across on the CMB sky, about 8 times the diameter of the full moon. And they carry a specific signature. The energy concentrated at the Hawking point produces an anomalously warm circular region in the microwave background. Not a cold spot, a warm spot, a thermal ghost of a dead black hole from a universe that existed before ours. In August of 2018, Penrose and 3 collaborators, Daniel Hahn at SUNY Maritime College, Krzysztof Meissner at the University of Warsaw, and Paweł Narowski at the Polish Academy of Sciences, posted a paper on Arxiv titled Apparent Evidence for Hawking Points in the CMB Sky. It was published in monthly notices of the Royal Astronomical Society in July 2020. The paper claimed to find exactly these anomalous warm spots in both the Planck and WMAP data. Daniel Hahn is perhaps the most unlikely figure in this story, and the one that best captures its strangeness. He is a mathematics professor at SUNY Maritime College in the Bronx, an institution best known for training merchant marine officers, not for probing the boundaries of observable cosmology. His PhD is from Stony Brook. His primary expertise is in mathematical physics and twistor theory, the geometric framework Penrose invented in the 1960s. He is the person who actually ran the numbers, who wrote the code, who scanned the CMB maps pixel by pixel, looking for the thermal ghosts of dead black holes. The contrast between the magnitude of the question, whether a previous universe left detectable evidence in our sky, and the modesty of the institution from which it was investigated, says something about how science actually works versus how people imagine it works. The biggest questions are not always answered from the biggest laboratories. The name Hawking points itself carries weight. Stephen Hawking had died on March 14, 2018, 5 months before the paper was posted. Penrose named the predicted CMB features after Hawking because Hawking radiation, Hawking's 1974 prediction that black holes are not perfectly black but emit thermal radiation through a quantum process near the event horizon, is the mechanism by which all black holes in a previous aeon eventually disappear. Without Hawking radiation, there are no Hawking points. Without Hawking's work, CCC's central prediction does not exist. The man whose science makes the theory possible did not live to see the evidence claimed in its favor, and he had, in 2017, signed the letter defending inflation against alternatives like CCC. The ironies compound. The statistical details matter here, because the argument that followed hinges entirely on them. Penrose's team identified the brightest Hawking point candidates by scanning the CMB maps and comparing them against 1,000 standard simulated skies generated from the Lambda CDM model. They found spots approximately 30 times brighter than the average CMB temperature variations. The signal appeared in Planck 70 GHz data and was independently confirmed in WMAP data. Their claimed confidence level was 99.98%. The Oxford Mathematical Institute announced that a powerful signal had been found that had never been noticed previously. Think about what that claim means if it is correct. Those warm spots are not random fluctuations. They are the last physical trace of black holes that existed in a universe before ours. Each one marks the location where a supermassive black hole spent longer than you can conceptualize, slowly converting its mass into radiation. And that radiation punched through the death of one universe and the birth of another to reach our instruments. It is the most extraordinary claim in modern observational cosmology. The fingerprint of a dead universe pressed into the oldest light in ours. This was not Penrose's first attempt at finding evidence for CCC in the CMB, and understanding the earlier attempt matters because it shows the pattern of claim and challenge that defines this entire field. In 2010, Penrose and Vahe Gurzadian of the Yerevan Physics Institute in Armenia reported finding concentric, low-variance circles in the WMAP and Boomerang data have the claimed 6 sigma significance. These circles, they argued, were gravitational wave signatures from colliding supermassive black holes in the previous aeon. The paper drew immediate fire. 3 independent groups published rebuttals within weeks, showing that similar circles appeared in standard Lambda CDM simulations. The circles were not a signal. They were a feature of the statistical properties of Gaussian random fields. Penrose and his collaborators refined the analysis. A 2013 paper by Meissner, Nurowski, and Roszczewski in the Proceedings of the Royal Society A reported a residual effect at 99.7% confidence. A 2018 paper by Anne, Meisner, and Narowski found a significant effect at 99.4% in Planck data. The concentric circles claim, unlike the Hawking points claim, has never been definitively settled. It sits in a frustrating limbo where the proponents see evidence and the skeptics see statistics. This pattern, claim followed by rebuttal, followed by refinement, followed by more rebuttal, is not a sign of bad science. It is a sign of science operating at the edge of what current data can resolve. The question is whether the next generation of data will sharpen the signal or dissolve it. The criticism of the Hawking points arrived quickly and struck hard. Dylan Zhao and Douglas Scott at the University of Toronto and the University of British Columbia published re-evaluating evidence for Hawking points in the CMB in the Journal of Cosmology and Astroparticle Physics in 2020. Their central point was the look elsewhere effect. When you scan an entire sky looking for the brightest spot at a particular angular scale, and you find one, you cannot simply report the significance of that spot in isolation. You have to account for the fact that you searched the whole sky and cherry-picked the most extreme result. When Zhao and Scott properly marginalized over ring size, the significance dropped from 99.98% to roughly 87%, about 1 sigma, a coin flip. They also showed that a standard simulated CMB map could produce a positive Hawking point at 5.2 sigma, exceeding the real data's peak of 4.8 sigma. When they computed the probability to exceed across all scales, 13% of simulations beat the real data. Their verdict was unambiguous. There is no statistically significant evidence for the presence of Hawking points in the CMB. Then came the machine learning. Yves Bodnier and colleagues at UC Santa Barbara built HawkingNet, a neural network based on the ResNet 1.8 architecture, and unleashed it on 50 million patch centers in the real CMB data using GPU supercomputing. Their results, published in the Journal of Cosmology and Astroparticle Physics in 2024, found no statistically significant evidence for Hawking points, but they added a caveat that is easy to miss and important not to. The absence of such features does not disprove the CCC model, they wrote. It implies that higher resolution CMB data or refined CCC-based predictions are needed. Douglas Scott, one of the harshest critics, was measured in his assessment. He said he would love for there to be evidence for a previous cosmic aeon, but it needs to be much better than presented so far. Ethan Siegel, the astrophysicist and science communicator, was not measured at all. He wrote that if this idea did not have the famous name of Roger Penrose attached to it, it would simply be another run-of-the-mill fringe idea. Penrose's team pushed back. Narowski responded to Siegel directly, arguing that the critic seemed to have never read the actual monthly notices paper and stressing that the statistical analysis met the highest astronomical standards. Penrose himself maintained that he welcomed attempts to explain the observations using standard models, but thought it would be hard unless radically new ideas came forth. In March of 2025, Meisner and Penrose published yet another paper introducing a gravitational wave epoch mechanism, further supporting CCC's predictions. And here is where you need to hold two things in your mind at once, because the honest reading of the evidence requires it. The Hawking points claim, after the look elsewhere effect, sits at roughly 1 sigma. That is not evidence. 1 sigma is indistinguishable from noise by every standard measure. But CCC is not the Hawking points claim alone. It is a mathematical framework that makes a prediction, and the prediction has not been conclusively ruled out, only shown to be not yet confirmed at the necessary significance level. The next generation of CMB experiments will measure the microwave background at far higher resolution and sensitivity. If Hawking points are real, they will emerge from the noise. If they are not, CCC will need to find a different observational signature or accept that its central prediction fails. That is how science is supposed to work. The problem is what happened in the gap between the claim and the resolution. Here is what happened. The anomalies in the CMB, the real, confirmed, independently verified anomalies that even the Planck team acknowledges, continued to sit there without an explanation, and the broader physics community, instead of investigating what those anomalies might mean, got into a war about whether the question was legitimate. Those warm spots, if Penrose is right, are all that remains of galaxies that once held civilizations, histories, libraries, music, grief, discovery, everything that fills a universe. Billions of years of existence, compressed into a thermal anomaly that most cosmologists are willing to dismiss as statistical noise, a few micro-Kelvin above the mean. That is what cosmic memory looks like. But the war over the beginning was not fought over Hawking points. It was fought over something much bigger and much uglier. And the man at the center of it is the last person you would expect to be there. On October 6th, 2020, the Nobel Committee in Stockholm announced that half of the physics prize would go to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity. He was 89 years old, one of the oldest Nobel laureates in the history of the prize. He shared it with Reinhard Genzel and Andrea Ghez, who had independently mapped the orbits of stars around Sagittarius A star, the supermassive black hole at the center of our galaxy. The irony was enormous, and everyone in physics saw it. The Nobel honored Penrose's most conservative work, his 1965 singularity theorem, a piece of rigorous mathematical physics that no one disputes and that Penrose himself considers a relatively straightforward application of differential geometry. It said nothing about conformal cyclic cosmology, nothing about Hawking points, nothing about the idea that Penrose considers his most important contribution to understanding the universe. In his Nobel lecture, Penrose discussed CCC anyway. He had said on the Nobel Prize podcast, simply, "I am very bad at giving up." Think about that for a moment. A man wins the highest honor in physics at the age of 89 for work done 55 years earlier, and uses his acceptance lecture to talk about the theory that the prize committee did not mention, because he believes the theory matters more than the award, because the anomalies in the CMB have not been explained, because the question of what came before the Big Bang, the question his framework was built to answer, remains open. And the reason it remains open has less to do with the strength of the evidence than with the politics of who gets to decide what questions are worth asking. The most dramatic intellectual reversal in modern cosmology belongs to Paul Steinhardt. He is the Albert Einstein Professor in Science at Princeton University, a title that itself carries a certain weight given the subject matter. In 1982, working with Andreas Albrecht at the University of Pennsylvania, he independently constructed the first workable model of cosmic inflation, the version called new inflation. which used a slowly rolling scalar field to drive the exponential expansion, and solved the graceful exit problem that had plagued Alan Guth's original 1981 proposal. Guth's version inflated forever with no mechanism to stop. Steinhardt and Albrecht's version, developed in parallel with André Linde's version in Moscow, found the exit. Together with Guth, Linde, and Hawking, Steinhardt was one of the 4 groups that first calculated how quantum fluctuations during inflation generate the scale invariant density perturbations that seed the formation of galaxies and galaxy clusters. He shared the 2002 Dirac Medal with Guth and Linde for his contributions. Steinhardt's journey from inflation's architect to its most prominent critic spans 3 decades and represents something rarer and more difficult than most people appreciate. Scientists are supposed to follow the evidence, but the social reality of science makes this extraordinarily hard when the evidence leads away from your own most celebrated work. Steinhardt did not wake up one morning and decide inflation was wrong. He spent years trying to make it work better, trying to solve the problems he could see forming. And when he concluded that the problems were not fixable, that they were not bugs, but features of the framework itself, he said so publicly. The professional cost was real. Colleagues he had worked with for decades signed a letter against him. Conference invitations changed. The whisper network of academia is subtle but effective. In 1983, Steinhardt became the first person to describe eternal inflation, calling it regenerative meta-cosmology. He had discovered, within the very framework he helped build, the feature that would eventually convince him to tear it down. The problem with eternal inflation is this. If inflation is eternal, if the inflaton field never stops inflating everywhere simultaneously, but instead spawns pocket universes endlessly, then it produces an infinite number of causally disconnected regions with different physical properties, different values of the cosmological constant, different particle masses, different numbers of spatial dimensions. Everything that can happen does happen, somewhere infinitely many times. And in an infinite multiverse, probability becomes meaningless. As Guth himself admitted, in an eternally inflating universe, anything that can happen will happen, and it will happen an infinite number of times. This is the measure problem, and after decades of work, nobody has solved it. Steinhardt saw this not as a feature, but as a fatal flaw. A theory that predicts everything predicts nothing. If inflation can produce any universe, it cannot be falsified by the observation of any particular universe. The idea that had dominated cosmology for 35 years had, in Steinhardt's view, committed the one unforgivable sin of science. It had become untestable. By 2001, Steinhardt had proposed an alternative. Working with Justin Curry, Bert Overud, and Neil Turok, he developed the ekpyrotic universe. From the ancient Greek ekpyrosis, the Stoic concept of cyclic fiery rebirth. In this model, the Big Bang is not the beginning. It is the result of a collision between higher dimensional membranes, brains, in the framework of string theory. Two three-dimensional brains, separated by a tiny extra dimension, approach each other, collide, and the energy of the collision produces the hot, dense state we call the Big Bang. The universe then expands, cools, eventually contracts again, and the cycle repeats. There is no singularity, there is no inflation, there is no multiverse, and there is something before the Big Bang. Neil Turok, Steinhardt's key collaborator on the cyclic model, brings his own remarkable biography to the story. Born in Johannesburg, South Africa, to parents who were anti-apartheid activists in the African National Congress. His father, Ben Turok, spent years in prison for his role in the resistance. Neil Turok grew up in exile in East Africa and London, eventually earning his PhD at Imperial College. He became a professor at Cambridge, then director of the Perimeter Institute for Theoretical Physics in Waterloo, Canada, one of the most prestigious positions in theoretical physics. He founded the African Institute for Mathematical Sciences, now a network spanning 6 countries across Africa, and won the 2008 TED Prize for that work. He currently holds the Higgs Chair of Theoretical Physics at the University of Edinburgh, and in a detail that feels almost too symmetrical to be coincidence, he also holds the Carlo Fidani Roger Penrose Distinguished Visiting Research Chair at the Perimeter Institute. The man who proposed one alternative to the Big Bang, named after the man who proposed another. Turok and Steinhardt published their joint vision in a 2007 book, Endless Universe, and continued developing the cyclic model through the 2010s. Their key observational prediction is that the ekpyrotic mechanism produces a nearly scale-invariant spectrum of density perturbations, matching the CMB observations, but generates an undetectably small amplitude of primordial gravitational waves. The tensor-to-scalar ratio in the ekpyrotic model is essentially 0. In inflation, most models predict a small but potentially detectable value. If future experiments push the upper limit on gravitational waves ever lower, without a detection, the ekpyrotic model becomes increasingly favored. The ekpyrotic model was attacked immediately and ferociously by the inflation community. The technical objections were real. Could the collision produce the right spectrum of perturbations? Could the bounce through the singularity be made rigorous? But the ferocity of the response exceeded what the technical issues warranted. What was really at stake was not a detail of perturbation theory. It was the credibility of the entire inflationary paradigm. The fight went underground for a decade, conducted in journals and at conferences, until February 2017, when it exploded into public view. Steinhardt, Anna Idjas, and Abraham Loeb published an article in Scientific American titled "Pop Goes the Universe." The title itself was a provocation, a play on the bubble nucleation mechanism of eternal inflation, but the content was more incendiary still. Its thesis was blunt. Inflationary cosmology, as we currently understand it, cannot be evaluated using the scientific method. They argued that inflation had become so flexible, with so many free parameters and so many possible models, that it could accommodate literally any observational outcome. If the CMB shows one pattern, there is an inflation model that predicts it. If it shows the opposite pattern, there is an inflation model that predicts that too. They accused the defenders of inflation of promoting the idea of some kind of non-empirical science, of accepting a theory not because it had been tested against data, but because it was mathematically elegant, widely believed, and had the right people behind it. The response was extraordinary by any standard and unprecedented in modern physics. On May 10, 2017, a letter titled "A Cosmic Controversy" appeared in Scientific American. It was co-authored by Alan Guth, David Kaiser, Andre Linde, and Yasunori Nomura, and signed by 33 physicists. The signatories included Stephen Hawking, Steven Weinberg, who had won the Nobel for unifying two fundamental forces. Edward Witten, widely considered the greatest living theoretical physicist, a Fields medalist. Lisa Randall, who had proposed extra-dimensional models of the universe. Lawrence Krauss, Leonard Susskind, the co-discoverer of string theory. Frank Wilczek, Nobel laureate for asymptotic freedom. George Smoot, Nobel laureate for measuring the CMB anisotropy. 4 Nobel laureates, a Fields medalist, some of the most accomplished scientists alive. They declared that inflation is not only testable, but that it has been subjected to a significant number of tests, and so far has passed every one. 33 of the most credentialed physicists on Earth, signing a public letter to defend a theory against 3 of their colleagues, is not normal scientific behavior. It is not how confident paradigms respond to criticism. Quantum electrodynamics does not need a letter signed by 33 physicists. General relativity does not need a public defense in a popular magazine. Theories that have been tested and confirmed respond to criticism with data. Theories that feel threatened respond with authority. And what Steinhardt had done, more than anything technical, was to threaten the authority of inflation by pointing out, in a public forum, that the emperor's mathematical garments were rather more adjustable than anyone wanted to admit. The exchanges that followed are worth studying closely because they reveal something about the state of cosmology that the public almost never sees. Alan Guth, the inventor of inflation, had been asked at a 2014 panel whether inflation is falsifiable. His response, captured on video, was remarkable. He said he thought inflation was a little too flexible an idea for that to make sense. He called the question silly. Steinhardt's team cited this directly in their rebuttal. The man who invented inflation, admitting on camera that it might be too flexible to falsify, while simultaneously signing a letter saying it is testable and has passed every test. Frank Wilczek, a Nobel laureate and signatory, later called the original Scientific American article very biased and said it bordered on slander. But he also confessed that he was uncomfortable with the idea of bringing some massive hammer of dissent down on the article and thought the response letter was possibly overkill. Lisa Randall, the Harvard physicist who signed the letter, had separately acknowledged that the model of inflation is incredibly unsatisfying. Peter Woit, the Columbia mathematician who runs the blog Not Even Wrong, offered the sharpest observation from outside the fight, replacing falsifiability by arguments about how many prominent people have signed your letter. He wrote, is a worrisome development. Steinhardt, Ijaz, and Loeb responded with a line that cuts to the heart of what was happening. Our point is that this kind of reasoning is inconsistent with normal science and cannot be resolved by invoking authority. And then there was the BIC, EP2 affair, which hangs over this entire story like a cautionary tale about what happens when a field wants an answer so badly that it stops checking its work. On March 17th, 2014, at a press conference at the Harvard-Smithsonian Center for Astrophysics, John Kovac announced the detection of B-mode polarization in the cosmic microwave background at a tensor-to-scalar ratio of R equals 0.20, disfavoring the null hypothesis at 7 sigma. The headlines were immediate and ecstatic. First, direct evidence of cosmic inflation. The smoking gun for the origin of the universe. Mark Kamienkowski at Johns Hopkins called it the smoking gun for inflation. Avi Loeb at Harvard called it the most important discovery in cosmology in decades. Max Tegmark at MIT said it was a Nobel-worthy discovery if confirmed. Stanford physicist Andre Linde was filmed being told the news by one of the BIC EP2 team members at his front door, and his emotional reaction, tears of joy, a champagne toast, went viral. Millions of people watched a physicist learn that his life's work had been vindicated. It had not. The problem was that BIC EP2 operated at a single frequency, 150 gigahertz, which made it impossible to reliably separate the cosmological signal from polarized emission by dust in our own galaxy. The BIC EP2 team had used preliminary, unreleased Planck data to estimate the dust contamination in their observation region. They extracted this estimate from a Planck presentation slide that had been shown at a conference and later posted briefly online. This is not how careful science is done. David Spergel at Princeton was among the first to raise the alarm, arguing publicly within days of the announcement that the signal could be galactic dust. Raphael Fauger and Colin Hill posted a detailed analysis suggesting the dust contribution had been drastically underestimated. By September 2014, the Planck satellite's full-sky polarized dust map showed that dust polarization in the BIC EP2 observation region was far higher than the BIC EP2 team had assumed. On January 30th, 2015, the joint BIC EP2 Keck Planck analysis was published. The signal was entirely attributable to dust. There were no primordial gravitational waves. The smoking gun was smoke. The emotional whiplash was immense. The viral video of Linda's tears became something else entirely in retrospect, not a moment of triumph, but a monument to premature celebration. The press conference, the headlines, the talk of Nobel Prizes, all of it evaporated. And what remained was a field that had revealed, in the most public way possible, how badly it wanted inflation to be confirmed. Kovac reflected afterward, with a line that is either admirably scientific or deeply revealing, depending on your perspective. He said he was not invested in any particular answer, and that whatever the universe says, he was going to be equally happy. The current best upper limit on the tensor to scalar ratio stands at r less than 0.036 at 95% confidence from the Bicep Keck 2021 data release. That is nearly 6 times lower than what BIC EP2 claimed to measure. The primordial gravitational wave signal from inflation, if it exists, is at least 6 times weaker than the dust that was mistaken for it. The BIC EP2 episode matters here for 2 reasons. First, it showed how desperately the inflationary establishment wanted observational confirmation. The emotional investment was immense, and the rush to announce before the signal was properly verified had consequences that the field still has not fully reckoned with. Second, and more importantly for this story, it revealed that the one prediction inflation makes that would definitively distinguish it from alternatives, the existence of primordial gravitational waves, has not been confirmed, and some alternatives, notably the ekpyrotic model, predict that those gravitational waves should be undetectably small. If future experiments continue to push the upper limit lower without a detection, the ekpyrotic model becomes increasingly favored over the simplest inflationary models. But this story is not ultimately about which model is right. The inflation wars matter because they explain why the anomalies in the CMB have not received the attention they deserve. The community's energy has been consumed by a territorial dispute over whether the standard paradigm is legitimate. And while the 33 signatories were defending inflation and Steinhardt was attacking it, the actual data, the confirmed, independently verified anomalies at the largest angular scales, sat there waiting for someone to explain them. And here is where it gets worse. Because while the inflation community was fighting about falsifiability, a group of physicists in a completely different field was quietly showing that the anomalies might be explainable, but only if you accept something that is in some ways even more disturbing than Penrose's dead universes. The irony of the inflation wars is that the energy spent defending and attacking the paradigm could have been spent investigating what the anomalies actually mean. Observational cosmologists who might have proposed targeted studies of the large-angle anomalies knew that the funding environment favored projects aligned with the standard model. Theorists who might have developed alternative explanations knew that their careers would be better served by working within inflation than against it. The sociology of science is not a conspiracy. It is a set of incentive structures that reward consensus and punish deviation. And in cosmology in the 21st century, those incentives have created a situation where the most interesting data in the field, the data that does not fit, receives less attention than the data that does. The anomalies do not need a champion. They need a research program. They need dedicated funding, targeted observations, and theoretical work that takes them seriously as evidence rather than dismissing them as noise. And that research program has been starved, not by malice, but by the gravitational pull of the paradigm. Loop quantum gravity starts from a premise so simple it sounds almost naive. Space is not continuous. It comes in discrete chunks at the smallest possible scale, the Planck length, roughly 10 to the negative 35 meters, about 20 orders of magnitude smaller than the radius of a proton. Area is quantized. Volume is quantized. The smooth fabric of space-time described by Einstein's general relativity is an approximation that works beautifully at large scales, but breaks down when you zoom in far enough, like a photograph that looks smooth from a distance, but is made of individual pixels if you get close enough. The framework was developed from a reformulation of general relativity that Abhay Ashtekar published in 1986, recasting gravity as an SU-2 gauge theory using what are now called Ashtekar variables. Ashtekar is the Evan Pugh University professor at Penn State and the founder of the Institute for Gravitation and the Cosmos. He was born in India, trained at the University of Texas at Austin under Robert Jerock and Bryce DeWitt, and spent decades building the mathematical infrastructure for a quantum theory of gravity that takes general relativity seriously on its own terms, without trying to force it into a framework borrowed from particle physics. Penrose himself has described Ashtekar's approach as the most important of all the attempts at quantizing general relativity. In loop quantum gravity, quantum states of space-time are described by structures called spin networks, first invented by Penrose himself in the 1970s for a completely different purpose, and later adopted by the LQG community as the natural language for describing quantum geometry. Nodes represent quanta of volume. Links represent quanta of area. The smallest possible area is approximately 6.3 times 10 to the negative 60, 6 square centimeters. The smallest possible volume is on the order of 10 to the negative 99 cc. Below these scales, space does not become denser or more compressed. It simply does not exist. There is no between the quanta. The fabric of space-time is not continuous. It is woven from discrete threads, and you cannot cut between the stitches. Carlo Rovelli, one of the founders of the field alongside Lee Smolin and Ashtekar, wrote a line about this that is worth pausing on. A spin network state is not in space, he wrote. It is space. The geometry of the universe is not a stage on which physics plays out. It is itself a quantum object, subject to uncertainty, superposition, and discreteness. When you ask where something is, you are asking a question about the spin network. There is no deeper answer. The network is the answer. The cosmological implications are built into the mathematics because space cannot be compressed below the Planck scale. The Big Bang singularity is replaced. Instead of a point of infinite density where the equations blow up and physics breaks down, loop quantum cosmology predicts a big bounce. The universe did not emerge from nothing. It emerged from a previous universe that was contracting, reached a maximum density, and bounced. The physics is captured by a modified version of the Friedmann equation, which is the equation that governs the expansion of the universe in standard cosmology. In the standard version, if you run the universe backward in time, the density increases without limit, and you hit a singularity. In loop quantum cosmology, there is a correction term that depends on the ratio of the energy density to a critical density, which is about 0.41 times the Planck density, roughly 5.1 times 10 to the 96th kilograms per cubic meter. When the energy density approaches this value, the correction term changes the sign of gravity. Gravity becomes repulsive. The contraction halts. The universe bounces. This was first shown by Martin Bojerwald, who in 2001, at the age of 27, published Absence of Singularity in Loop Quantum Cosmology in Physical Review Letters while working as a postdoctoral researcher at Penn State under Ashtekar. It was the founding paper of the field. Bojerwald showed that when the quantum corrections are taken into account, the classical Big Bang singularity is resolved. The universe does not emerge from a point. It transitions from a collapsing phase smoothly through a quantum bridge at the Planck density into an expanding phase. The singularity is not avoided by fiat. It is avoided by the physics. The discrete structure of space itself generates a repulsive force at extreme densities that overpowers gravity and reverses the contraction. In 2007, Bojerwald published a landmark paper in Nature Physics titled "What Happened Before the Big Bang?" that went further. Using semi-classical states in the loop quantum cosmology framework, he showed that the pre-bounce universe had a space-time geometry otherwise similar to that of our universe today. Not a bizarre alien geometry, not a chaotic quantum foam, a universe expanding, then contracting, then bouncing, then expanding again. The implications were stark. Our Big Bang was not a creation event. It was a phase transition, and the universe on the other side of it was recognizably a universe. But Bojerwald also discovered something troubling, something that connects back to the deepest themes of this entire story. He called it cosmic forgetfulness. The bounce acts as a kind of information filter. Some properties of the pre-bounce universe pass through, others are scrambled. There is a quantum uncertainty principle at work across the bounce that limits what can be known about the universe that came before. Specifically, Bojerwald showed that there is a complementarity between the precision with which you can know the volume of the pre-bounce universe and the precision with which you can know the matter content. You can know one well, but not both. The bounce remembers, but imperfectly. And the imperfection is not a limitation of our instruments. It is a feature of the physics. The universe itself does not retain a complete record of what came before. Ashtekar and collaborators, Tomasz Pawlowski and Paramkrith Singh, put the framework on rigorous footing in their 2006 trilogy of papers, published in Physical Review Letters and Physical Review D. They demonstrated that the Big Bang is replaced by a quantum bounce occurring specifically at Planck scale density, and that the quantum state of the universe evolves deterministically across the bounce. There is a well-defined sense in which the universe before the bounce is a physical reality, not a mathematical abstraction. Singh later extended the result to show that the bounce is robust across different matter types and different choices of quantum ambiguity parameters. It is not an artifact of a particular model. It is a generic feature of the quantum geometry. And then came the result that connects this entire story back to the anomalies in the sky. In 2015, Ivan Agulo at Louisiana State University published a paper in Physical Review D showing that the CMB's hemispherical power asymmetry, the anomaly confirmed by both WMAP and Planck, one half of the sky carrying more fluctuation power than the other, could have originated from a cosmic bounce preceding inflation. The mechanism is specific and technical. Quantum perturbations evolving across the bounce develop strong non-Gaussian correlations between observable scales and superhorizon modes. These correlations produce a dipole-dominated modulation on large angular scales. The predicted pattern matches the observed asymmetry. Then in July of 2020, Ashtekar, Brajesh Gupt, Donghui Zhang, and V. Srinath published Alleviating the Tension in the Cosmic Microwave Background using Planck scale physics in Physical Review Letters. This paper showed that loop quantum cosmology naturally explains two of the most significant departures from the standard model simultaneously: the suppression of power at the largest angular scales and the lensing amplitude anomaly. Both arise from Planck scale corrections to the initial conditions of inflation. Gupt said something about this that captures the vertigo of the result. A Planck length is about 20 orders of magnitude smaller than the radius of a proton, but corrections to inflation at this unimaginably small scale simultaneously explain two of the anomalies at the largest scales in the universe, in a cosmic tango of the very small and the very large. Agulo put it differently, but no less strikingly. It proves, he said, that physical processes occurring in the remote past, before the inflationary epoch, can leave observable imprints in the sky. Before the inflationary epoch, before the Big Bang. The sentence passes quickly, but the implication does not. If Agulo and Ashtekar are right, the CMB anomalies are not flukes. They are data. They are measurements of something that happened before this universe existed, and they have been sitting in our satellite data for 2 decades, published, confirmed, and largely ignored. What makes the loop quantum cosmology results different from Penrose's Hawking points is the strength of the statistical connection. Penrose's warm spots, after the look elsewhere correction, sit at 1 sigma. Agulo and Ashtekar's explanation of the hemispherical asymmetry and the power suppression does not depend on finding a specific signal in the data and then arguing about its significance. It starts from the theoretical framework, derives what the framework predicts for the CMB at large angular scales, and shows that the predictions match the observed anomalies. It is a top-down calculation, not a bottom-up search. And the match is not approximate. The predicted suppression of the angular power spectrum at the lowest multipoles and the predicted amplitude of the hemispherical asymmetry are both consistent with what Planck measured. This is not proof. It is consistency. But it is the kind of consistency that makes the 1 sigma Hawking points result look like a supporting detail rather than the main event. The case for pre-Big Bang physics does not rest on a single contested signal. It rests on a pattern, and the pattern is emerging from multiple independent directions. And there is a prediction. Loop quantum cosmology forecasts specific power suppression in B-mode polarization at large angular scales. The Japanese space agency JAXA is building a satellite called Lightbird, targeted for launch in fiscal year 2032, designed to measure B-mode polarization across the entire sky with a sensitivity of delta R equals 0.001. The Simons Observatory in Chile's Atacama Desert achieved first light in February of 2025 and is already taking data. Its 6-meter telescope scanning the sky from an altitude of 5,200 meters. CMB S4, a ground-based experiment combining resources from the entire CMB community with up to 1 million detectors spread across multiple sites in Chile and the South Pole, is expected to begin observations in the late 2020s. And LISA, the European Space Agency's space-based gravitational wave detector, adopted in January 2024 with construction underway, will launch around 2035 and open the millihertz frequency band, the band where pre-Big Bang gravitational wave signatures would be strongest. Within a decade, we will have instruments sensitive enough to test whether the anomalies in the cosmic microwave background carry the signature of a universe that existed before ours. The experiment is being built. The data will come. The only question is what it will show. And the data that has already arrived from instruments that were not designed to look for pre-Big Bang physics is already making people uncomfortable. In June of 2023, the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, announced the detection of a stochastic gravitational wave background using data from 67 pulsars observed over 15 years. This was the first evidence of gravitational waves at nanohertz frequencies, wavelengths so long they take years to complete a single oscillation. The standard explanation is that this background is produced by merging supermassive black hole binaries scattered throughout the universe, but the amplitude and spectral shape of the signal have features that are difficult to explain with mergers alone. Multiple groups have pointed out that a cosmological component, gravitational waves produced in the very early universe, possibly during a pre-Big Bang phase, could contribute to or even dominate the signal. Gasparini and Veneziano's 1993 pre-Big Bang scenario, built on string theory, specifically predicts a blue-tilted gravitational wave spectrum that would peak at high frequencies, but leave a detectable tail at nanohertz frequencies. The NanoGrav result is not evidence for a pre-Big Bang universe, but it is consistent with one, and it was not expected. Then there is the James Webb Space Telescope. JWST was not designed to study the CMB or test pre-Big Bang models. It was designed to observe the first galaxies, but what it found when it started observing them has created a different kind of problem. In its first year of science operations, JWST discovered an abundance of massive, well-formed galaxies at redshifts above 10, corresponding to times less than 500 million years after the Big Bang. These galaxies are more massive, more luminous, and more mature than the Lambda CDM model predicts should exist at those early times. The standard model says the universe should not have had enough time to assemble such large structures so quickly. Some of these galaxies have stellar masses exceeding 10 billion solar masses at redshifts above 12. The tension is real and growing. It does not, by itself, point to pre-Big Bang physics. It points to something wrong with our understanding of how the early universe evolved, and that something may include the initial conditions set at the Big Bang, conditions that all of the pre-Big Bang models propose are inherited from what came before. The string theory contribution to pre-Big Bang cosmology deserves a mention here because it completes the picture of how many independent lines of theoretical physics converge on the same conclusion. In 1993, Maurizio Gasparini and Gabriele Veneziano proposed a model in which the Big Bang is not a beginning, but a transition from a cold, empty, expanding state called the string perturbative vacuum through a violent, high curvature phase to the hot, expanding universe we observe. The driving force is the dilaton, a scalar field that is an unavoidable consequence of string theory. Before the Big Bang, in this model, the dilaton rolls from weak coupling to strong coupling, and the universe contracts and heats up until it reaches string scale temperatures and bounces. Separately, Robert Brandenburger and Kamran Vafa proposed in 1989 that the reason we live in 3 spatial dimensions rather than the 9 or 10 predicted by string theory is that in the hot, dense, early universe, only in 3 dimensions could the winding modes of strings efficiently annihilate each other, allowing those dimensions to expand while the others remained compactified. Both of these models require something before the Big Bang. Neither has been confirmed, but both make predictions that the next generation of gravitational wave detectors, particularly LISA, could test. The convergence is the point. These are not fringe theorists working in isolation. These are independent research programs using different mathematics, different physical frameworks, and different assumptions, arriving at the same structural conclusion. The Big Bang was not the beginning, and the evidence, statistical and contested and frustratingly ambiguous, is already in our data. But here is what keeps me up at night about this entire story. And it is not the anomalies, and it is not the politics, and it is not the question of which model is right. It is what all of the models agree on. Penrose's conformal cyclic cosmology, Steinhardt's ekpyrotic model, Ashtekar and Bojewald's loop quantum cosmology, the Gasparini-Veneziano pre-Big Bang scenario from string theory, Brandenburger and Vafa's string gas cosmology. They disagree on nearly everything. They disagree on the mechanism. They disagree on the mathematics. They disagree on the role of inflation, the nature of the bounce, the structure of extra dimensions, the fate of information. They fight about these disagreements in journals and at conferences, and occasionally in the pages of Scientific American. But they agree on one thing: the Big Bang was not the beginning. Something came before, something physical, something real, something that obeyed laws and contained structures and evolved over time, not a metaphysical abstraction, not a philosophical conjecture, a universe. And the question that none of these models can escape, the question that follows inevitably from the premise they all share, is what happened to it. In Penrose's framework, the answer is the most explicit and the most devastating. The previous aeon lasted for an almost inconceivable duration. Stars formed, burned, and died. Galaxies coalesced and evolved. Perhaps civilizations rose, built, discovered, loved, suffered, and created meaning in all the ways that conscious beings create meaning. And then, over timescales so vast that the current age of our universe is a rounding error, the stars winked out, the galaxies dispersed. Black holes grew, consuming everything around them, and then began their own slow death by Hawking radiation. A supermassive black hole, the kind that sits at the center of a galaxy like our Milky Way, takes roughly 10 to the 100th power years to evaporate. Write that number out. A 1 followed by 100 zeros of years. The current age of the universe, 13.8 billion years, is approximately 10 to the 10th power. The evaporation time is not 100 times longer or 1,000 times longer. It is 10 to the 90th power times longer. There is no analogy that makes this number meaningful. It is longer than anything you have ever tried to imagine, by a margin that is itself unimaginable. And when the last black hole evaporates, when the last photon of Hawking radiation joins the thinning bath of light that is all that remains, the universe enters a state that is both the simplest and the strangest in all of physics. There is no matter and no mass. There are no clocks, no rulers, no way to distinguish here from there, or now from then. The universe, despite being infinitely large and unthinkably old, becomes, through the mathematics of conformal geometry, equivalent to a single point. And that point is the next Big Bang. Everything that happened in the previous aeon, every galaxy, every star, every planet, every act of creation or destruction, every memory and every loss is gone. Not destroyed in a cataclysm, not burned or crushed or blown apart, conformally erased, rescaled out of existence. The universe does not end with a bang or a whimper. It ends with a mathematical transformation that makes the question, what happened, meaningless, because the framework in which happening was defined no longer applies. And what survives? Penrose says that almost nothing survives. The one thing that crosses the boundary, the one physical trace of an entire cosmic history, is the concentrated Hawking radiation from the final stages of black hole evaporation. Those Hawking points, those faint warm spots in the CMB of the next aeon, a few microkelvin above the mean temperature, spread across a disk 4 degrees wide, detectable only by instruments of extraordinary sensitivity, distinguishable from noise only by statistical methods that the experts cannot agree on. That is the memorial. That is the legacy. Everything that existed in the previous universe compressed into a data point. Penrose has written about this with the matter-of-fact calm of someone who has spent decades staring at an implication until it stopped being shocking and became simply true. He describes the Hawking points as the last physical traces of the most massive objects that existed in the previous aeon, not the most complex objects, not the most interesting objects, not the objects that anyone in any meaningful sense would choose to preserve, the most massive, Black holes are entropy sinks. They are the universe's garbage disposals, consuming complexity and excreting thermal radiation that carries no recoverable information about what went in. The only thing that survives the death of a universe is the record of its most destructive objects doing what they do best. The civilizations do not survive. The science does not survive. The art does not survive, and only as warm spots in someone else's static. There is something profoundly wrong about that, in a way that is not captured by any equation. The universe does not preserve what is valuable. It preserves what is massive. The selection criterion for cosmic memory is not complexity or beauty or meaning. It is gravitational dominance. The universe remembers its monsters, and there is a deeper problem here that none of the models can escape. It involves the arrow of time and the nature of memory itself. Within any given cycle, within any single aeon or bounce or ekpyrotic collision, the arrow of time is well defined. Entropy increases. Cause precedes effect. Memories form of the past, not the future. Eggs break, but do not unbreak. The asymmetry between past and future, which we experience as the fundamental texture of reality, is maintained. But across cycles, the arrow of time becomes something stranger. In CCC, the crossover between eons is not a moment. There is no time at the crossover surface. The concept of duration loses meaning when there is nothing with mass to serve as a clock. The transition from one aeon to the next is not an event that happens at a particular time. It is a mathematical identification of two surfaces that are formally identical despite describing, from within each aeon, radically different physical situations. One is the infinite future. The other is the Big Bang. They are the same surface, and there is no time between them, because the concept of between requires time, and time requires mass, and mass does not exist at the crossover. In loop quantum cosmology, the bounce happens in a finite but almost unimaginably short duration of Planck time. The arrow of time appears to reverse through the bounce, in the sense that the contracting universe's entropy increases toward the bounce, and the expanding universe's entropy also increases away from it. The bounce is an entropy minimum. It is the most ordered state the universe passes through. And from the perspective of observers on either side, if such observers could exist at Planck density, the arrow of time always points away from the bounce. Both sides experience their universe as expanding from a low entropy beginning. Both sides would, in principle, think they live after the Big Bang. Neither side would be wrong. This has an implication that is genuinely disturbing to think about carefully. If you were in a universe on the contracting side of a bounce, approaching the moment of maximum compression, from your perspective, time would be running normally. Entropy would be increasing. Your memories would be forming in the usual way. The universe would appear to be expanding. You would have no way of knowing you were on the contracting side. And at the moment of the bounce, the moment of transition, there would be no discontinuity in your experience, because there would be no you to experience it. The Planck density state erases the structures that constitute consciousness long before it erases the physical degrees of freedom that constitute space-time. You would not experience the end of the universe. You would simply stop existing at a moment you could not distinguish from any other moment. In a universe you could not distinguish from one that had a future. The question this raises is not a physics question. It is a question about you. If the universe is cyclic, if this has happened before and will happen again, and if nothing of substance survives the transition, then what does it mean that anything exists at all? The standard secular answer to the question of cosmic purpose is that the universe does not have one. That meaning is something conscious beings create for themselves within the time they have. But cyclic cosmology adds a layer to this that the standard answer does not address. It is not just that the universe has no purpose. It is that the universe has a mechanism for rendering everything you do, everything anyone does, not just meaningless in the abstract, but physically undetectable. The erasure is not a philosophical statement. It is a prediction. It is something the equations say will happen. In loop quantum cosmology, the bounce preserves the quantum state of the universe. So in principle, information about the pre-bounce universe is encoded in the state that emerges afterward. But Bojewald's cosmic forgetfulness means that the encoding is lossy. The bounce scrambles some of the information. What passes through is not a memory. It is a blur. The new universe carries the imprint of the old, but cannot reconstruct it. Like a palimpsest, where the original text has been scraped away and written over, leaving only the faintest ghost of what was there before. In the ekpyrotic model, the collision between brains produces a clean slate. The energy of the collision thermalizes, producing a hot, dense state that is essentially random. The previous cycle structures are not preserved. They are converted into heat. The arrow of time, the distinction between past and future, is maintained within each cycle, but the content of each cycle, the specific history of what happened, is erased and rewritten. In every model, the conclusion converges. Something came before, and almost nothing of it survived. And so the question is no longer what came before. The question is what will come after, and whether any record of anything that has ever happened in this universe will survive the answer. This is not a question about cosmology. It is a question about you. If any of these models is correct, then 14 billion years from now, or 100 billion, or 10 to the 100th power, this universe will end. Not suddenly, not violently, slowly, imperceptibly, through the gradual dimming of every light and the patient evaporation of every remaining structure. And what will survive of everything humanity has ever done, every cathedral and every equation and every act of kindness and every war and every child born and every song written, is at best a faint thermal whisper in someone else's sky. Penrose calculated the probability of our universe's low-entropy Big Bang occurring by chance at 1 in 10 to the 10 to the 123. That number is not a number in any meaningful sense. It is an absurdity dressed in mathematical notation. And Penrose's answer to the absurdity is that it was not chance. It was the result of the previous aeon's black holes systematically destroying gravitational entropy over timescales that dwarf comprehension. The low entropy of the Big Bang, the very thing that makes our universe capable of supporting structure and complexity and life, was purchased by the death of everything that came before us. You exist because a previous universe was slowly, completely erased. Your consciousness, your ability to wonder about this, your awareness that you are hearing these words, is built on the ash of a cosmos that was ground into nothing so fine that even its geometry forgot it existed. And one day, incomprehensibly far in the future, the same thing will happen to us, not because of some failure, not because of something we did wrong, because this is what the universe does. It creates and it sustains, and then it erases. And the eraser is not a flaw in the system, it is the system. The erasure of the old is the mechanism by which the new is born. The death of everything is the engine of everything. The anomalies in the cosmic microwave background may be the evidence. The warm spots, the cold spot, the hemispherical asymmetry, the axis of evil, each one a scar, a trace, a whisper from a universe that no longer exists in any form we can detect or reconstruct or mourn. Published in the highest impact journals in astronomy, confirmed by 2 independent satellite missions with a combined cost in the billions of dollars, and treated by the community whose job it is to explain them as tensions, footnotes, appendices. There is a generation of experiments being built right now, at this moment, in the Atacama Desert, and in clean rooms in Japan, and in laboratories across Europe that will determine whether those whispers are real. Lightbird, CMB, S4, the Simons Observatory, LISA. Within 10 years, we will know whether the cosmic microwave background carries the imprint of a universe that existed before ours. And if it does, you will have to sit with what that means, not just for physics, for you, for the permanence of everything you have ever cared about, for the question of whether anything you do, anything anyone does, leaves a mark that lasts. The data has been sitting there for 20 years. The satellites measured it. The teams confirmed it. The papers were published, and then the field moved on because the implications were too large and too uncomfortable and did not fit inside the model that everyone had agreed was correct. Roger Penrose is 94 years old. He is still publishing papers about conformal cyclic cosmology. In March of 2025, he and Meissner posted a new paper introducing a gravitational wave epoch mechanism that extends CCC's predictions into regimes that future detectors could test. He is still claiming that the warm spots in the CMB are the thermal ghosts of black holes from a previous universe. He is still being told, politely and sometimes not politely, that the evidence is not significant enough. In his Nobel interview, he described his relationship to CCC with a kind of understatement that only the English and only the very old can manage. "I am very bad at giving up," he said. The man who proved that singularities are inevitable, who helped establish the modern understanding of black holes, who invented twistor theory and the Penrose tiles and the Penrose triangle, who won the Nobel Prize for work done when Lyndon Johnson was president, considers the question of what came before the Big Bang his most important work, and the field has not yet decided whether he is right. Paul Steinhardt is still at Princeton. He is still developing the cyclic model. He is still arguing that inflation is unfalsifiable and that the alternatives deserve more attention and more funding and more institutional support than they receive. The 33 signatures still hang over the field like an unresolved chord. The anomalies are still in the data. The experiments that could settle the question are being built. He may be wrong. They all may be wrong. The warm spots may be noise. The anomalies may have mundane explanations that we have not yet found. The concentric circles may be an artifact of Gaussian statistics. The hemispherical asymmetry may be a fluke. The cold spot may eventually be explained by a supervoid we have not yet properly mapped. That is possible, and it is the safe position. It is the position that requires No revision to the standard model. No uncomfortable questions about what came before. No reckoning with the implications of a cyclic universe for the permanence of everything we know. But consider the alternative. Consider that the oldest light in the universe is carrying a message, and that the message is this: you are not the first. You will not be the last. And when your universe is done, when every black hole has evaporated and every photon has redshifted into silence, the only thing that will remain of everything you have ever known is a faint, warm spot in someone else's sky. A spot that their scientists will argue about. A spot that will appear in their data at some confidence level that may or may not clear their significance threshold. You will not be remembered. You will be a data point that fails to reach significance. And there is nothing in any physics we currently understand that can prevent this.